up in the morning, kinda bankroll. Ay, 10 chains on like Django. She said you so out of pocket. Walk around 100K in your pocket. Ay, 150 for the show now. Can't
Hello, everyone. Today is Unit 7, Lesson 5. We're going to be talking about conductors and insulators. But before we start talking about some of this new content, I want to go over together some of the key takeaways from yesterday's circuits investigation. So, there are three basic requirements for a functioning circuit. These requirements are, first, an energy source. So that would be the battery in your circuit, for example. Second, you need a closed conducting pathway where the charge can flow. So in the activity you did, you used wires to create a closed loop within your circuit. And then finally, you need one or more loads that use energy. So a load is like the thing that your circuit is actually powering. So in the activity you did, we had light bulbs. So that would be your load, where your charges are depositing their energy to be transferred into some other kind of energy, like light energy, for example. So I want to bring us back to this idea of a closed conducting pathway as it relates to something that we call current. So the closed conducting pathway is needed in order for charge to flow in a continuous loop, right? So charge is constantly flowing throughout our circuit. And the rate at which charge flows past a given point in the circuit is defined as the current, which we symbolize with the variable I. And so we can actually draw, a lot of times when people talk about electricity, they'll draw an analogy to water. So if we want to think about, for example, what we mean when we say a river has a high current, that would mean that there's a lot of water flowing through the river very fast, right? That's a high current. And the same thing is true for electricity. If you have a lot of charge flowing past a point within a given time period, you would say that that circuit has a very high current. And of course, the units for current are going to be amperes, which we symbolize with this capital A. The closed pathway must extend from the positive terminal of the battery all the way back around to the negative terminal. Charges are leaving the positive terminal with a certain number of joules of potential energy as determined by the voltage of the battery. When they go through the external circuit, that energy is used by whatever the load is. So that might be a light bulb like we were using yesterday. Then the charges have no energy. They come back around to the negative terminal, wherein the battery does work on each charge, again, to add whatever amount of joules of potential energy. And this energy source, the battery, creates the difference in potential that causes the charge to spontaneously flow from high to low potential. I also want to show everyone before we move on an example of what a circuit diagram should look like. So this is Tyree's work here. You'll see that he has drawn his switch. It's open in this diagram, but we know that if we close that switch, then our current will start to flow. He has his resistor represented with these like zigzag lines there. That's the symbol for resistor. And then he has his light bulbs in these little circles. And then finally, he has this battery. The positive terminal is going to be the longer line, and the negative terminal is going to be the shorter line. So now that we're done going over what we learned yesterday from our investigation, we're going to switch gears and talk about Unit 7, Lesson 5. So your notes should be titled Conductors and Insulators. So let's start by thinking about conductors. A conductor is a material that allows electrons to flow freely. So charge flows very easily through a conductor. This is because the atoms that make up conducting materials have valence electrons or outer electrons that are loosely bound and free to move from one atom to another. Because electrons are going to repel each other, right? We know that like charges repel. If we add a certain amount of external energy to cause just one electron to move, right, away from its atom, this one move can set off a sort of domino effect which causes all the electrons down the line to continue to repel one another and move throughout the entire length of the conducting material. An insulator, on the other hand, is a material that's going to resist the free flow of electrons. So charge will not readily or easily flow through an insulator. The atoms of insulating materials hold very tightly onto their outer electrons. So they're really holding tight onto those valence electrons. And those electrons, therefore, are not going to freely move throughout the material. So we won't see the same cascading effect where we can send a bunch of charge throughout the material like that. So let's actually think more about what this looks like on the molecular level. So here is a diagram that depicts the difference in the molecular structure between a conductor and an insulator. So you'll see for the insulator you'll see for the conductor on the left that we have a bunch of free electrons floating around. So these free electrons are not tightly bound to the outer shells of these atoms. And then if we look at the insulator on the other hand, we can see that these electrons are actually fixed into the outer shells of the atom. So for the conductor, those electrons are going to be able to move freely throughout the material. And the same thing is not true for the insulator because those atoms are holding on to their outer electrons very tightly. And here we have some examples of both conductors and insulators. So some common conductors would be silver, gold, copper, steel, and seawater. Actually, seawater is salty. So we see that metals actually make great conductors, and that's why they're often used as wires. And then if we look at our insulators, we have rubber, glass, oil, diamond, and dry wood. So that's pretty interesting. So these insulators would be materials that prohibit the free flow of charge.